Hello everyone. Today we are going to discuss a question from stereochemistry where organic and inorganic both kind of molecules we have taken. And this question is basically about the axis of symmetry as well as optical activity, which we are going to test whether our compound is going to have these things present or not. We have been given these different 8 molecules and we had to see which of these are satisfying both of these conditions, optical activity and axis of symmetry. The answer to this question comes out to be 5. We'll be discovering which 5 and how these 5. Here we go. So we have rephrased our question. This question should have been identify the number of molecules from the following which are having C2X of symmetry as well as they are optically active. The compounds given over here, this is cisplatin and this is dibromoylene. We have 1,3-dibromoylene. We are having some cobalt-ene and chlorido complex, that was cis, and this is cobalt-diene and ethylene-diamine and dibromido complex, that was trans, and then we are having trans 1,2-dichlorocyclopentane, that is organic compound, and we are having this tris oxalatoferrate. We are having cobalt EDTA complex, and we are having cis tetramine dichlorido platinum complex. We'll be naming these all compounds so that later we can be finding reference to these compounds very easy. So this is numbering from 1 to 5, and then there is 6, 7, 8. These are 8 different compounds. Out of these 8 different compounds, we have seen the answer was 5. Which 5 we are going to now see. These compound number 2, this is going to be optically active, and C2X of symmetry, this compound is also optically active. Compound number 5 is also optically active and having C2X of symmetry. Compound number 6 and compound number 7. These are the compounds which are going to satisfy the condition. So this was the answer. Now we'll be going a little deeper into all these details of these different compounds. So first of all, this question is literally on higher level of difficulty. Of course, it is going to be, because we are going to see the axis of symmetry, not just the optical activity. Both the things we have to look into. Also here, the important point to note is the misconceptions number of students have is that axis of symmetry can be the condition of optical activity. It is not, because there are many molecules. Actually, in our given example, all the 8 molecules are having at least one C2X of symmetry present, and this C2 axis of symmetry has nothing to do, not only just C2, it can be C3, C4, C5, C6, whatever. Any axis of symmetry has nothing to do with the optical activity of a given compound. This is one important point which has been tested in this particular question. So if someone has got any ambiguity, they may not be getting this question correct. The second important point is that to show optical activity for a given compound, these 3 elements, plane of symmetry, center of symmetry, and AAOS, that is alternating axis of symmetry. It is not the axis of symmetry. We call this as alternating axis of symmetry, which is responsible. Sometimes we are calling this alternating axis of symmetry as rotation reflection symmetry. Rotation reflection. That's because if you're rotating some molecule by any axis first, then you have to see the reflection from the perpendicular plane of that particular axis, and then you have to relate the starting compound and the final compound. That is the meaning of AAOS, which is alternating axis of symmetry. So if any of the molecule does not have these 3 things, plane of symmetry, center of symmetry, and alternating axis of symmetry, then only our compound is going to be optically active. Okay, fair enough. Now we'll be seeing these one by one in detailed discussion for every single compound, why this is having C2X of symmetry and why this is optically active or inactive. Here we go. So the first compound we are going to take is the cisplatin. And before that, this is the comparison table, like which compound is going to be optically active and which compound is going to be optically active. If you note over here, all these 8 compounds which we have been given are actually having the C2 axis of symmetry. In optical activity, some of these are, some of these are not. So N is for no, Y is for yes, N is for no, N is for no. Three compounds over here are having the optical inactivity, and all these are having at least some plane of symmetry. The first compound, the fourth compound, and the eighth compound, they are having the axis of plane of symmetry is present. Because of plane of symmetry, these compounds are going to be optically inactive. Rest all 5 compounds are optically active. Yes, yes, yes. Sorry, not yes. This one was not yes. So second was yes, third was yes, fifth was yes, sixth was yes, and seventh was yes. Now we'll be seeing these one after another, how there is C2 present and why this is optically active or inactive, one by one as we go further. About the first compound. We know this compound is going to be having dsp2 hybridization, so this is going to be flat. Because it is flat, the molecular plane is going to have one C2 axis of symmetry like this. So if you are basically rotating this molecule by along this particular C2 axis, what we have shown, this molecule is going to look like this. And we can see the first compound and second compound, they are exactly identical. We have shown that NH3, NH3 and Cl here with different colors for the sake of clarity, that when this rotation has been done, then which chlorine is appearing where. Actually both the Cls are chlorine only, both the NH3 is amine only. So it doesn't matter whether they are colored or not, they are identical. For the sake of simplicity, we have shown this different colors in the different ligands throughout this question. Okay. I hope that's clear. There's no any confusion in this part, because this is very much clear that this is C2 axis of symmetry. This is going to be, and because this is having a plane of symmetry as well, this is not going to be optically active. Second compound was 1,2-dibromoallene. Allenes we have learned are going to be, if you are having just 2 double bond accumulated, they are going to be perpendicular, like one plane and then one perpendicular plane. Those kind of things are going to be present. We knew that this molecule is going to be optically active because there is no plane of symmetry present, no point of symmetry present, no alternating axis of symmetry was present in this compound. Now the question is how this compound is having C2 axis of symmetry. Many of these students are not able to see that C2 axis of symmetry very easily. So here we go. We are trying to see with the help of some model which can be looking like this. So what we have tried to do is we have tried to put this allene inside a cuboid. And what we have done, this bromine comes over here, this hydrogen comes over here, this bromine goes on to the left, this hydrogen comes over here. Now, where is the axis of symmetry? What we are trying to do is we are trying to see the axis of symmetry here. So we see here basically one plane which we are trying to represent, that C2 axis, this one we are trying to say, and where it passes through. We can understand this from the fact that we have got some diagonal planes which are connecting two hydrogen atoms. So think about this hydrogen and this hydrogen is being connected, and then the back side of that, if these points also we connect, we will be getting some plane, this kind of plane. Along that plane, if we pass an axis which is touching the central carbon atom, this sp2 hybrid carbon atom, this is touching that atom, and this is passing through the face center of the front face and the face center of the back face as well. If you see from that viewpoint, if you rotate this by 180 degree across that, what will happen, this hydrogen from one particular corner of this rectangular face will be going to the opposite corner of rectangular face if you are rotating by 180 degree. That's very much evident. We can see it probably very clearly. And the same thing will happen for the opposite face, because this chlorine which was present onto the one corner, if we are rotating this particular plane by 180 degree, then this chlorine will be reaching onto the diagonal corner. That is very much obvious. And also you can see when we'll be rotating this molecule along this particular axis, then This chlorine, because this is being rotated by 180 degree completely, then this hydrogen, this carbon, and this carbon will be switching their places. So this is our C2 axis of symmetry. Okay, little bit difficult to comprehend, but with this cuboid, this can be very easily seen. Probably, I believe you can visualize that, and you try rotating that along that particular axis, and you can see, sorry, how hydrogen can be moving and how bromine can be moving, and they will be swapping their places after rotation by 180 degree. That's for sure. Okay, moving to the third molecule. This is going to be cis, we'll say bis ethylene diamine dichloride cobalt 3 compound. This compound as can be drawn something like this. So what we have done is, because this was cis, we have tried keeping both the chlorine onto the cis positions over here. This is the first chlorine, this is the second chlorine, they are cis to each other. And now we have put the CH2 and H2 again onto the cis position. This is CH2 and H2, and this is NH2, CH2, CH2, and another one. Now if you're thinking about this possible plane, sorry, this possible axis which is passing through this square plane, if you flip it along this particular axis, what will happen? As we have been seeing earlier in cisplatin, the chlorine from here will appear onto this side, and this chlorine from the back side will be coming onto the front side. And the same thing is happening for the two NH2s which have been drawn in color, because this NH2, when we are flipping this 180 degree, this is basically, we can assume this was a kind of horizontal flip. The C2 axis can be leading with respect to our molecule, something we can visualize as horizontal flip. So in horizontal flip, this NH2 which is coming onto the front right now will be going onto the backwards, and this NH2 which is onto the back side with respect to this axis will be coming onto the front side. That is how this is going to be the axis of symmetry. If you can visualize this axis of symmetry, visualizing the axis of symmetry in the compound number 6 and compound number 7 will be very, very easy. Okay. Moving to the next molecule. This is the molecule from the previous situation only, like the third molecule only. The only difference is that one was cis, this one is trans. So what has changed? One thing they have given us differently, that rather than being a chlorine present in the earlier case, now there is a bromine present. That hardly affects the stereochemistry. So how this is going to be? Again, we can go by that same reasoning. If you are having one bromine on the top, one bromine on the bottom. So if the C2 axis we are rotating, this is going to be a kind of horizontal flip. We can visualize things very much clearly. Both the bromine will be swapped by each other. The 2NH2 shown in red onto the back side will be coming onto the 2NH2 onto the front side, and the same thing happens for the two other NH2 as well. So this is going to be the conversion of this molecule into that which is identical. This is going to be a C2 axis of symmetry, which is twofold axis of symmetry for this particular case. So this compound is not going to be optically active because this is going to have plane of symmetry as well. That plane can be passing through the two bromines, or it can be bisecting the square plane, and there can be even more possibilities bisecting the CH2-CH2 linkage across the cobalt Br bond. This is very much planar molecule. This is going to be optically inactive for sure. Fair enough. Going to the next molecule. This is our trans 1,2-dichlorocyclopentane. So the situation is, when the previous molecule in octahedral complexes, when we are having two bidentate ligands, we are keeping trans. This is going to give us symmetric situation. Now in the case of cyclic rings in 3-membered, 4-membered, or 6-7-membered rings, when we are having cis compounds, they tend to have more they will be relatively more symmetric in nature, and when we are converting them into trans, they can be going into less symmetric state, as we can witness in this particular example. See here what is happening. So when we are having this chlorine present on cis and trans fashions, now this molecule on its this molecule cannot be superimposed onto its mirror image, number one. Number two, If you are rotating this by 180 degree, this we have been calling as the two-fold axis of symmetry as well. So if you rotate this molecule, this is again going to be the kind of horizontal flip or horizontal flip across this plane of this molecule. This is going to be same as the axis of symmetry, the way we have shown it. So what will happen? The CH2 from here will be going over there. The Cl coming on the top will be going onto the bottom. The Cl, which was earlier going onto the bottom, will be coming onto the top. These molecules are going to be interconverted into one another, or we can say these two molecules are basically identical. This is going to be the C2 axis of symmetry for this compound, and this compound was optically active as well, because if you draw its mirror image, this is not going to be superimposable onto that. So non-superimposable mirror image, no plane of symmetry, no center of symmetry, no alternating axis of symmetry, because if we have rotated this molecule and we've seen the reflection from the perpendicular plane, the two molecules will not be identical. That's why you're saying this molecule is optically active. This is optically active. This also had C2 plane that we have just seen, right? The next molecule is going to be the trisoxalatoferrate. In this trisoxalatoferrate, what we are seeing is the oxalate groups are present now. So as we have done in the earlier cases, this oxalate we are keeping in the plane. Let us say this is the plane of that square thing. This one, what we are seeing, this is the square plane. With respect to that plane, this oxalate can be kept in the same plane. So when we'll be flipping about this C2 axis, this COO, that oxalate ring is going to be here only in that you can say horizontal flip. What only changes is this C double bond O oxalate, which was coming front side, is going into the backward side. But this does not affect our situation because both the carboxylate groups are, both C double O groups are identical. And then also one carboxylate which is going on to the backward side from here, when we are doing horizontal flip, that will be coming over here, front side. And in horizontal flip, this C double bond O, which is coming right now front side towards us, will be going away from us when the horizontal flip has been done. So this is again going to be a C2 axis, which is passing from the molecule in the plane, bisecting our square as shown in the diagram. Okay, so this was having C2 axis, and this was also optically active, because this time there is no plane, no point, and no alternate symmetry possible, because this C double O linkage is going to be present in such a way this is not going to be symmetric. And this is actually very interesting case, because students sometimes find that this is going to be the example of MAA thrice kind of molecule. So they believe because this ligand was symmetric, this molecule has to be symmetric, because if you are passing from one of the carboxylate, then there should be this molecule should be divided into two identical halves. That's not true. Molecule can be cut into two halves, but they are not mirror images of each other, because in the plane of symmetry the condition was the left half and right half, or the top half and bottom half, or whatever way you cut it, the two halves must be mirror images of each other. So if you say you are cutting your molecule from, say, the square plane, let us say we are cutting this molecule from this particular plane, this oxalate onto the right, copper, oxygen may be cut into half, but on the front side, whatever we are getting, this backside carbon is having one bond coming above. This would have been plane of symmetry if this linkage was not coming from this carbon, this linkage was coming from that carbon, then only, because this thing does not have any mirror on that side, the bottom side, right now in this molecule. If you break this bond and make this C double bond O attached over there, something like that, then this plane, the square plane, this one is going to be a plane of symmetry. That's not the situation. This bond goes backward, backside, away from us. This bond comes front side towards us. There is no mirror image of this on the top half, or there is no mirror image of this thing in the bottom half. Such a molecule, when we are having MA thrice, such molecules are not symmetric. These compounds are all optically active, irrespective of what kind of ligand we might have taken. So whatever ligand you take, these compounds are asymmetric, and they are optically active. We have been seeing here the C2 axis that's there. We have seen that already. Moving on to the next molecule. A little bit complicated it may seem. Here we go. So this molecule is actually kind of the previous molecule, only just a little bit more complicated it seems. Complicated in the sense that this is your CH2CH2N, that EDTA ligand we already know, that is ethylene diamine tetraacetate. So this is ethylene thing over here, this is ethylene thing, and this is diamine. If this would have been if this nitrogen was having both the hydrogens present. What has been done, both the hydrogens have been replaced by CH2COO, CH2COO on this nitrogen as well as onto this nitrogen, CH2COO and CH2COO. And now what we have done, earlier when this was the square bond, we have kept these two nitrogen, and acetates we have split. One acetate goes on the top, one acetate goes onto the bottom of the octahedral thing, and one acetate linkage goes onto the backside carbon to the left, and one acetate comes front and goes onto the top side onto the left. This is our cobalt EDTA complex. Now if we talk about this particular axis, again we do horizontal flip, we'll see that particular axis what we have represented, this axis is going to be a C2 axis, because if you rotate by 180 degree, you will find this molecule is going to be looking identical. This is not any way different. The only difference over here we have tried to elaborate is showing those groups with different colors so that you can see the CH2N group which was coming towards us earlier will be going backwards. And also this COO group which was coming towards us will be going into the backward side after horizontal flip, and this C double bond O which was backside is coming onto the front side. Also we have tried to elaborate that this carboxylate which is on the top in this first one, after C2, this axis of rotation of rotating by 180 degree, this is going to be at the bottom. So this first molecule, this one, and the second molecule after rotation by 180 degree are identical. This axis is going to be called as the C2 axis or twofold axis of symmetry. That is very, very clear. Okay. The last molecule here we are having, that is very much straightforward. We are having 4 ammonia and 2 chlorine. And this was told this is cis. So because it was told to be cis, we have put both the chlorines onto the closer positions. Now again, just like rest of the molecules, we are doing the horizontal flip, keeping the 2 ammonia on the top and bottom. They will be swapped, they will be identical, and 1 chlorine from the front, this goes onto the back side, another chlorine from the back side comes front, that is as it is, and this NH3 goes onto the back side, that NH3 comes over here, molecule number 1, molecule number 2, exactly identical after rotation by 180 degree. This is going to be our C2x of symmetry. So that was the question. Very detailed explanation we have done. I hope you understood each and every single point for every single molecule. If it helped you, please consider supporting this channel. Thank you. Bye bye. Have a great time.